Hi there. Glad you could join me again. Trying out a new audio setup. See if you can hear some background noise. That's alright. Sometimes that gives me more tingles than not. Let's continue where we left off. Find the right page here. We're going to start today with a practice question. Just a good old mechanical pencil today as we refocus. Let's see what we can do with this question. After an airplane takes off, it travels 10 kilometers to the west, 9 kilometers north, and 2 kilometers up. So we're thinking about 3 dimensions, a 3-dimensional problem. How far is it from the takeoff point? So what we really care about is its displacement. How far is it from before this to after this? Okay, let's draw a picture. "10 kilometers to the west. 9 kilometers north. And 2 kilometers up." I'm going to draw that like that. Okay, let's think. What we really need to know, we have here a right triangle, or at least the beginnings of a right triangle. And we can imagine that the 2 legs of this journey, the first 2 legs, form a triangle just like that. And once we figure out what this length is, we know have this height of 2, we can figure out what the full journey displacement was. So let's think. Once I figure out how long this length is, I'll have this part of a new triangle, this part of a new triangle, and I can find out from here to here, which is our full displacement, and that's the question: how far is it from here to here? Great. There, let's do that. So let's figure out what this length is. We're going to use our old friend, Pythagorean Theorem. A squared plus b squared equals c squared. 9 squared is 81. 10 squared, 100. 100 plus 81, 181, naturally. And to get c by itself, we can take the square root of both sides. Need to pull out the calculator, good old trusty friend. (181). Let's find the square root. There it is. 13.4. 13.45. Alright. Now we know the length of this side. Now how does that help us? Let's remember. The point of the question is to figure out how far it is from here to here, which is up off the table. And to do that, we need to figure out how long the vector is from here to here. Now, we solved this length by making a triangle out of these two legs. Let's do the same thing, but now we have this leg, and we can solve for this leg. Okay? So I'm actually going to turn this on its side now. I'm going to draw another smaller example triangle, where this hypotenuse represents the distance from here to here, which tells us the bottom is 13.45. And this length right here is going to be 2. Now we can use Pythagoras again. 2 squared plus 13.45 squared equals c squared. Let's do it again. 2 squared is 4. Let's do this. 13.45 squared. Of course, I totally forgot. 181. How silly of me. Equals c squared. 185 equals c squared. Let's take the square root of both sides quickly. And square root again. 13.6. So that tells me the distance from here to a point up here 2 kilometers off the page is going to be a total distance of 13.6, which makes perfect sense because it's more than this, and it's certainly more than this. Okay, that's great. We should be well familiar with that so that we can now move on. Alright, let's zoom out a little bit. Try to get some more real estate on this page. Oh, pay no mind to the disused Pokemon card. Let's get that out of the way. Shoot. Go on. Yeah, get out of the way. Alright. Let's take a drink right here. The bulk of today's lesson is going to be a rather simple lesson about unit vectors. Alright, what is a unit vector? A unit vector is a vector with magnitude 1. So we're talking about little tiny vectors, little baby vectors. And we're going to say that these have no units. They are dimensionless. They only represent a small direction, a very small vector pointed in a certain direction. So for example, and going forward, the x direction, left and right, will be represented by the unit vector little I. Okay? And we're not going to draw a dot. Instead, for this unit vector, we're going to draw triangles. Okay? So this unit vector with little I and a triangle, it represents a very small vector of magnitude 1 pointed in the x direction. Okay. Certainly, if we wanted to, we could say negative I. Alright? And we can use this in several calculations, which we're going to do in the future. Now in the y direction, a vector in the y direction with unit 1, or with magnitude 1, will be lowercase j, and we can certainly as well have negative j. Alright. Now for the z direction, we're going to say this is going into the page and out of the page. And this is, we're going to use naturally k. So we have k, and we have negative k. Great. There. Okay. So the reason this is important, the reason we can use this is because we can use this for all sorts of calculations when we just need to care about the vector. For example, if we needed to multiply something so that its direction worked out, we could always multiply by 1, just like you can do in math. Just like you can do in math, if we multiply 10 times 1, it still stays 10. And the same way, if we have a vector and we multiply by this vector, it's just 1, but the direction could change, and that could be very beneficial to us. That could be a tool in our toolbox. Okay. So let's do this. Let's go back to our old friend. It's going to be the vector A. Last time we expressed A in terms of its components, A sub x and A sub y. Okay. Now here's what we're going to do instead. AX and AY are really just the same as A x vector I plus AY vector j. Okay, and that's the same thing. Just helps us describe. This is vector A in terms of its components, and it also expresses directions. Okay. All in all, the vector A, any vector really, can be expressed in terms of 3 components. So, in general, a vector A, any vector, but in this case A, any vector, will be described as, can be described as A sub x little I vector, AY little j vector, and a z little k vector. Okay. In the same way, just to give another example, vector B, bxi, oops, excuse me, that's not right, byj, and bzk. When you see x direction, you should always think little I. When you see y direction, you should always think little j. And when you see z direction, you should always think little k. Okay. And the reason why we have to introduce this little zk is because what if our vectors don't lie in the xy plane? They may lie in the xyz coordinate space. Alright. Let's try a practice problem. Excuse me, got lost in an ASMR reverie. Pardon me. Let's continue. Let's consider 2 vectors. We have vector D. Oh, my lead's running out. Alright, vector D. Vector D is magnitude 6 in the x direction. Notice I'm using my unit vector I, plus magnitude 3 in the y direction. Notice I'm using unit vector j, minus 1k. And you know what? All these unit vectors don't have dimensions, but that doesn't mean we can't add dimensions. Let's call it meters. These are displacements. Likewise, magnitude, or vector e, is composed of 4i minus 5j plus 8k meters. Now what does this mean? It means 6 across, 6 across, 3 up, and 1 out. What does this mean? It means 4 across, 5 up, and 8 out, so way out here. Okay. Those are displacement vectors. Recall that if we are looking at this vector d, 6 to the right, 3 up, 1 out, 1 in, because negative, so 1 into the page. And this is 4 across, 5 down, 8 out. So we care about the total displacement from the beginning of here to the end of here. Okay. We want to know the magnitude of the displacement from vector d to vector e. And you know what? Just to make things a little more challenging, a little more interesting, let's multiply this by 2. We're going to say 2d to e. What does that look like? Let's see. Let's think. We're going to call this new vector a, our old friend vector a. And we're going to say that a equals this. So, let's look. 2 times our vector d, because 2d, so we're going to plug in vector d, minus, pardon me, this is not an arrow, this is a minus sign, 2d minus e. Okay, let's see. We want to treat this like an equation, 2d minus e, so 2d minus 1 copy of e. Alright. Now, what are we going to do with this 2? Well, here's what we're going to do. We're going to distribute. We're going to take this 2 and multiply it all the way across. And I'm going to write it very small because I'm running out of room. 12i plus 6j minus 2k. Okay, great. Minus 4i minus 5j plus 8k. Okay. Now, in the same way that we distributed this 2, we also need to distribute this minus. Okay? Because that's going to become a bit troublesome later on. Let's look. We're going to rewrite this as it is. We're going to distribute the minus. So instead of minus, it's going to be plus. We're going to take everything and multiply everything by minus. So, minus 4i plus 5j, careful, minus 8k. Okay, great. Now, we're going to, this is like one long equation. We are going to combine like terms. So 12i minus 4i. Okay, 12i minus 4i is going to be 8i. Okay. 6j plus 5j is going to be positive 11j. Minus 2k minus 8k minus 10k altogether. Okay. There it is. And that's great. And our final vector is going to look just like this. Okay. A bit jumbled, a bit less organized than I would like, but I think you get the idea. We can use and multiply vectors just like variables. We can put vectors in for any letter and multiply it just like we do with numbers and minutes, just like we do with any variable. We can say, oh, the variable d, it actually represents this vector, not necessarily just a number. Instead, it represents this whole vector, this whole story it represents. So if we were to take this and say 2d minus e, we can plug in this to d and this to e, and then we can solve, which is what we just did, and we get an answer. What does this equal? 2d minus e, 2 of these minus 1 of these? Well, here's what it equals. 8i plus 11j minus 10k. Okay. Next time, we're going to start again with one more practice problem. Maybe some more of this, because I almost gave myself tingles just doing this right here, looking at the camera. Well, maybe we'll do some more of this, because this seems, this is quite stimulating. Yes. Alright. I'd like you to do me a favor, leave a comment that says what you'd like to see in these videos. What kind of pencil, what kind of paper, what kind of miscellaneous accoutrement that I have around. Because the candy was an experiment, this will be an experiment, this will probably be back. And I can always touch the camera, and I can do normal, ASMR type stuff. We're going to see what happens. You tell me what you want to see. Alright. So long. Farewell. When we come back, we will see more to do with vector and vector multiplication. Alright. Maybe some more of this. Let's see. We'll see. I don't know. It'll be a surprise. Goodbye.